This is a 37th Flow seminar. My name is Samuel Horvat, and together with Peter Ihtarik, Virginia Smith, Avrelin Bellat, and Dan Alistair, we are the organizer of Flow Seminar. For those of you who doesn't know about the seminar, Flow Seminar stands for Federated Learning One-Word Seminar, and it was created as a global online forum for the dissemination of latest scientific research in all aspects of federated learning. This includes both theory and applications, and areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization systems, hardware, and many more. For today's talk, it's my great pleasure to introduce you our speaker, Maruan Al-Shedivat. He's a PhD student in the machine learning department at Carnegie Mellon University, advised by Eric Thing. He has also spent some time at OpenAI and Google Research, and today he's going to talk about his work on an inferential perspective on federated learning, and he's also going to talk about remarks on data efficiency of meta learning. So thank you, Maruan, for accepting to give a talk, and the stage is yours.
Thank you, Sam. Thank you for the introduction, and thank you for inviting me to give a talk at the seminar. It's great to be here, I'm going to talk today about this inferential perspective on federated learning, some work that I've been doing very recently, as well as remarks on data efficiency of meta learning. These are actually two separate papers that I'm gonna talk about today with collaborators that you see on the slide. Each of them are sort of independent from each other, but both of them are related to federated learning in one way or the other. So I thought I'll give a talk about both at the seminar, and hopefully some of the audience will find each of those papers interesting in one way or the other. So the first part of the talk, which will take maybe 25 to 30 minutes, will focus on standard federated learning and specifically on this inferential perspective. And the second part will be shorter, and it will focus on discussion of personalized federated learning. All right, so let me get started right away. And I should mention, feel free to ask questions in the chat or just interrupt me whenever. Actually, if you ask a question closer to the slides that I'm presenting, it'll be easier for me to answer. So I'm pretty sure, since this is the Flow seminar, everyone is very familiar with the formulation of federated learning, but nevertheless, I'm gonna just write down some notation and introduce the problem. So typically, federated learning is thought as a distributed learning problem or distributed optimization problem, and it's usually formulated as given on the slide, where we're trying to optimize this objective function, which is called the global objective function, which is a sum of some weighted local objective functions. And the weighted local objective functions are also known as the client objectives, are given on the slide as the sum over the data points of the clients. So the idea of federated learning is to try to learn from a data set that is scattered across a lot of so-called clients, which could be organizations, or it could be mobile devices, IoT devices, etc. And typically, we assume that we don't have access to the data on these clients. And so the server doesn't have direct access, but the server wants to be able to learn a model parameters data by interacting with these clients. So the typical approach to solve this problem is called federated averaging. So this is the standard algorithm today, and it essentially optimizes this global objective over multiple rounds of communication between the server and the clients. So this is how it goes. So initially, the server would request from a population of clients, and let's say population of clients are mobile devices. It will request some clients, and we'll get a few of them to participate in a training round with the server. So the server will start by distributing some state of the model to these clients. The clients will initialize their models with the state. We'll do some local optimization, for example, run local SGD, and then compute some deltas between the obtained model states, local model states, and send them to the server. The server will try to aggregate those, and then the next round begins after that. So there'll be a sequence of these rounds where the server communicates with subsets of clients and tries to optimize this loss function or the objective function. Now, I think it's important, before starting to look into any federated learning problem, to sort of set the stage with the modeling assumptions that we're making here. There are so many different formulations of federated learning right now, so it's really I think it's extremely important to understand which actual problem we're trying to solve. So the problem that we're trying to solve in this paper is called cross-device federated learning. Right, so the idea here is that there's a large population of client devices which are memory limited that are trying to communicate with the server over multiple rounds and trying to optimize some model. So the assumption is that there is about 10 to 1,000 clients that participate per round. The population of clients is humongous, so there could be multiple millions to a billion of these clients in the population. And that the communication of the model between the server and the clients is the actual bottleneck of the whole process, right? So you can see that there is this selection process where some of the clients indicate to the server that they are available. The server has to select the subsets of these clients, then it has to configure them, and then training happens, and then there's this reporting stage and aggregation on the server. So in order to execute a whole round, there's a bunch of work that happens before and a bunch of work that happens after actually the clients make steps, right? So taking SGG steps on the clients is pretty cheap compared to sort of executing more rounds throughout training. Right, so just to summarize what I just said in a bunch of assumptions that we're making in the setting is that there's a very large population of clients. We typically can see each client at most once throughout the whole training, just because we're selecting 10 to 1,000 clients from multiple millions, and it's very likely that a client will be selected at most once. So data distribution is typically non-IID, and this is one of the sort of distinguishing properties of federated learning. Would like to learn from extremely heterogeneous data sets scattered across all of these clients. Now, as I said, increasing the number of steps per client is relatively cheap, and also increasing the number of clients per round often is also cheap, right? Just parallelizing this communication is extremely cheap compared to trying to increase the number of overall the number of rounds. So if we would like to, if we know, after realizing that client-server communication is slow and expensive, the question that we can ask ourselves is, how can we speed this up, right? And a reasonable answer, probably everyone already might have guessed this, right, is that we can just simply increase the amount of local computation that clients do because it's extremely cheap. So we can increase that amount of computation maybe by an order of magnitude, maybe by 2 orders of magnitude, and make these clients actually locally make more progress in terms of optimization per round, and therefore reducing the total number of communication rounds that is necessary to achieve certain performance of the model. So an interesting puzzle that we ran into while looking into this a bit closer is that as a result, if we increase this amount of computation on the clients a lot, the convergence, the model will eventually converge to an inferior point. So the fixed point, basically, of federated averaging will be different from the sort of global optimum of this objective, even in the very simple cases such as convex objectives or even quadratic objectives. So just to illustrate this on a very, very toy example, and I think this is the most simple and minimal example that is, sort of illustrates this problem very vividly. So let's imagine we're trying to solve a least squares problem where we have a response variable y, which linearly depends on some features x. There is this theta, which is model parameters, and there is some noise, right? And we're trying to recover this model by simply minimizing the L2 loss, right? And well, this is equivalent to minimizing this quadratic given on the slide. And so if we have some data set on one client and another data set on another client, we can plot in the parameter space. And in this case, it's 2D, the contours of the objectives of these clients, right? And we can see that there are local optima, right, of each of these clients. And there is this global optimum. And importantly, this global optimum, in fact, can be anywhere on this plane, right, depending on how these matrices, right, matrices A, determine sort of the skewness and rotation of these quadratics. So in a sense, you can figure out, we can find for any point basically on this plane, you can find matrices A1 and A2 and B1 and B2 such that you can sort of align these objectives so that the global optimum will be anywhere on this plane. So what we're going to look at is we're going to run federated averaging on this problem. I'm going to look at the distance to the global optimum as a function of the number of rounds, right? And if we run this for federated averaging with different number of local steps at each round, we're going to get roughly this curves. So in this animation on the left-hand side, we start from different initial parameters on this plane, right? And then we just trace the trajectory as well as the distance to the global optimum. So what we can see pretty clearly is that, sort of centralized optimization or mini-batch SGD in the end beats all of these federated averaging algorithms, even though initially the speed up is pretty clear, right? By increasing the number of local steps, we can actually speed up convergence initially very fast, but we will converge to some suboptimal point. And so the question is like, why does this happen? And there are a couple of answers. So last year, I think in the summer, a couple of preprints came out that try to explain this in the case of quadratic losses. And the one paper I'm aware of is by Pathak and Wainwright, which eventually appeared in Europe's 2020, that showed pretty much the same problem for federated gradient descent, right? So there's no SGD, no noise for federated gradient descent with multiple numbers of sort of local steps, right? And then they show that the centralized least squares optimum, right, looks like this. And the federated averaging, or federated GD in their case, with multiple steps, which they denoted E, has this fixed point, right? So clearly, even visually, these two fixed points analytically look very different. Now, another paper by Charles and Konechny, which is going to appear at ASS 2021, essentially analyzed the same problem, also federated quadratics, and they showed again that as we increase the number of steps, in this case denoted K, we're going to converge to worse and worse sort of point in terms of the model value. Right, and the takeaway was that they took from there that federated averaging as well as FedProx and other methods that they actually optimize some surrogate objective. So in this paper, they characterized that surrogate objective. They actually gave an expression for it, and I'm not giving it on the slide just because the expression is a bit complicated. And they show that there is a gap between the optimum, between the surrogate objective and the global optimum, right? And if we go back to this illustration, right? So there is the gap between the fixed point of our federated averaging and the actual global optimum. So both papers proposed a fix, right? So the first fix was proposed an algorithm similar to scaffold, and scaffold is a variance reduction algorithm that was designed specifically for federated learning that solves this problem. Without going into details, the algorithm uses stateful clients. So it assumes that all the clients have some state, they preserve the state, and when they interact with the server, they will update their internal state somehow and then use that state to later on compensate for the so-called client drift, right? So they don't sort of pull the server towards a suboptimal solution, right? And another assumption that they make is that throughout training, all the clients have to be accessed multiple times in order for this sort of state to play any role in the optimization. Charles and Konechny proposed another solution, which was basically careful fine-tuning of the client learning rate and the server learning rate, right? So both client and server and federated averaging have certain learning rates, and what they showed is that if we tune the schedules, right, not just the rates, but the schedules of how we decay these rates, we can reduce this discrepancy between the fixed points, right? So in a sense, those approaches solve the problem, right? So you can train faster and at the same time find a way to converge to that global optimal point. But we try to look at it from a different perspective and ask the question: are we actually solving the right problem in the first place here? Maybe there's another formulation of the problem that would allow us to have a consistent objective function that we can optimize. So we started looking at the problem, right, that is typically formulated as an optimization problem from an inference perspective. So in this case, we'll look at these. We're trying to optimize this objective function called f, right? And oftentimes this f is simply a negative log likelihood of the data given the model, right? So what is negative log likelihood? In the case of classification, it's our standard cross entropy loss, right? It's the negative log likelihood under a Bernoulli model, right? Or under a binomial model. So the solution basically to this problem essentially is the maximum likelihood estimator, right? Because it's just an expectation over local likelihoods and then an expectation over the clients. Together will be just the likelihood over all the data that is available in the system. So an alternative to MLE, instead of just trying to solve directly for a maximum likelihood estimator, which is just a point in the space of parameters, we can try to infer the full posterior distribution over the parameters. Right, so this object is called the posterior distribution, where we condition on data that we observe, and we're trying to infer this distribution over parameters of the model. And it factorizes into likelihood multiplied by prior. You might ask, what kind of prior should we assume here? Well, even if we don't assume any prior, right, under the uniform prior, the mode of this posterior will be essentially equal to the maximum likelihood estimate. Right, so essentially if we can solve this problem, which is arguably more complex because we're trying to represent a much more complex object, we should eventually recover the solution to the original problem. Now, why would we solve a more complex problem? Now, interestingly, posterior distributions have this nice multiplicative decomposition, which is exact, right? So any posterior distribution multiplicatively decomposes into a product of subposteriors, right? And these symbols denote proportionality. So there should be a product of local subposteriors multiplied by some constant. So it means that, well, if we are able to decompose the global posterior and we're able to infer local posteriors, we can follow the algorithm that is sketched out on the slide, right? Instead of trying to directly optimize this global posterior, we could try to ask every client to approximately infer their local posterior, communicate some information about their local posterior to the global server, and then ask the global server sort of to multiplicatively aggregate all of this and find the mode of this global posterior. And in that case, this mode will be our global optimum, right? So simple, but the key point is that we need to be able to do this efficiently, right? It's a complex problem. Posterior inference is usually intractable, and we need to go through multiple approximations to be able to execute this, not only just execute this computationally feasibly, but also in this distributed federated setting where we have constraints on communication and local computation as well. And so our paper is trying to tackle this problem. And just as an example, let's go back to federated quadratics, right? So in federated quadratics, again, we have this quadratic loss on each client, which is essentially what I'm showing in this derivation is that it's essentially the log likelihood under the Gaussian model, right? So I can decompose quadratics and I can have this essentially Gaussian plus constant that depends on the data. Now, the global posterior will be the product of Gaussians, which is also a Gaussian, right? And each of these local Gaussians will have precision matrix, which will be xi transpose xi, and the corresponding mean vector. And the solution to our problem in a fully quadratic Gaussian case can be actually written down analytically, right? So this is precisely the expression mu that was obtained by Pathak and Wainwright when they characterized the standard least squares regression. So it's a very well-known thing. The only thing is that is different here is maybe these weights that are proportional to the number of points that we have on every client, right? So clients can have different amounts of data, and we should weight these corresponding terms proportionally to the amount of data on each client. So the approach that we're going to take in this paper is that we'll try to infer this posterior modes, right? And if we're able to do that, if we can get this mu hat, we'll sort of solve the problem, right? So we'll have this local posterior covariances. We'll need to infer local posterior means as long as we're able to infer them and communicate them to the server, which will sort of aggregate and be able to compute this mu. We're done, at least in the quadratic case, right? Now, if we're not in the quadratic case, you can think of this as sort of Gaussian approximations to the posteriors. So if you've heard of variational inference, right? In variational inference, people try to, one of the goals is to approximate the posterior distribution that is very complex, non-Gaussian, and cannot be represented analytically. So instead of trying to compute it exactly and compute all these integrals that posterior estimation involve, we can try to approximate it with tractable Gaussian approximation. And this is exactly what we're going to do here, right? So even if the true posterior is not Gaussian, we'll still try to approximate it with local Gaussians and assume that the global posterior is also Gaussian. So in that case, mu will not be exactly the solution, but at least in the quadratic case, it is. And the hope is that even in the non-Gaussian case, it will be closer to the actual solution than the fixed point of federated averaging. So we'll see. We'll see if that works later on. But for now, we actually run into a bunch of challenges, even just looking at this expression on the slide, right? It's pretty simple, but it's pretty challenging also when we think about models that are realistic, right? Let's say we want to optimize a neural net that has millions of parameters. The question is, how can we infer this local posterior over a vector that is million dimensional? We need also the covariance matrix that is million by million, right? And we need this mean vector that is million dimensional. And eventually we need to also estimate this matrix inverses that are just intractable. And so we're going to address these challenges one by one in the next few slides. So first, let's talk about the local posterior inference. So there's apparently a relationship between a stochastic gradient descent and approximate Bayesian inference. And the key idea is that if you run SGD on the likelihood, then at some point after you sort of converse, SGD starts sampling approximately from the posterior distribution, right? So SGD on the log likelihood approximately after some burn-in number of steps will start sampling from the posterior distribution. So the idea that we're going to pursue here is that we're going to try locally still run SGD, and at some point we're going to treat SGD iterates as samples from the posterior distribution. So using these samples, we can estimate the mean of the posterior as well as the covariance matrix, right? And the paper that is given on the right actually justifies this and studies the quality of stochastic gradient-based MCMC. Right, so the algorithm is pretty simple, right? So it's simply 11 lines of code, right? We're going to run a loop first of client optimizer on the client, right, for some number of steps B. We'll discard these samples and call them burn in, and then we're going to sample, right? And we're going to produce L samples. And to produce each sample, we're going to run our optimizer for just K steps and simply average the trajectory of the iterates of SGD. So what happens here is that at the end of this, essentially, if the total number of this calls to the client optimizer is the same as in federated averaging, is equal to basically the number of steps the federated averaging takes locally, essentially computational cost on the client is going to be identical to federated averaging. Right, but at the end, we're going to produce a bunch of vectors instead of just a single vector. Now, in order to be able to infer this global posterior, the mu hat that we're after, we're going to slightly change this problem and approach it from a different perspective. So instead of trying to invert the matrix, actually, we're going to convert it into an optimization problem. Right, we can denote some of these matrices as A, and some of these vectors as B. And we know that mu hat is actually the minimizer of this simple quadratic. And so we can ask the server, instead of trying to invert this huge matrix, simply iteratively solve this quadratic over multiple rounds. Right, so the idea here is to solve the intractable inverse using SGD, right? And in this case, I'm giving the equations for the gradient descent on the slide, but you can see that we have the sum right, over all the clients here. And obviously, in the case when n is many, many millions of clients, we can only work with subsets of clients per round. So instead of taking the full gradient step, we can actually approximate it with a stochastic gradient step, right? Simply subsample the clients. Now, the difference, and very interestingly, this update actually is equal to the update of federated averaging, except one little thing is that federated averaging uses a different, computes these deltas, these local client deltas differently. So instead of computing a matrix inverse multiplied by some vector, it simply computes the difference between the initial state at round t and some updated state, client specific state, right? Theta it. So in a sense, it also solves our communication problem, right? So initially we thought that, well, maybe we need to take both statistics, this covariance matrix as well as mu, and communicate from the clients to the server. That would have been intractable because, well, it will be a quadratic number in the dimensionality of the model. And if the models are big, that will just throttle the network and will not be able to communicate as fast as we are in federated averaging. Now, the final part, right? Essentially, we solved on the slide. Essentially, we solved the problem, right? Except one last part, we need to be able to compute these deltas, right? Delta i's. And the question is, how can we compute a matrix inverse, which is extremely high dimensional, right? Multiplied with a vector, right? And do it on device, on the client, right? It's if we're in any reasonable setting, right, we will have a million dimensional model. This is just impossible, right? We need some kind of approximation. So one approximation that comes to mind is, well, we can approximate this matrix diagonally, right? And inverse of a diagonal matrix, we can represent diagonal matrix simply as a vector, and inverse, computation of this inverse is trivial. And in fact, what we show in this paper, I apologize, what we show in this paper is that we can compute these deltas, right, exactly with this matrix inverse and time and memory that is linear in the number of dimensions. And this is probably one of the main technical contributions of our paper. Specifically, we formulated it as a theorem, right? Given L approximate posterior samples from theta 1 to theta L, and given that mu is the sample mean and sigma L is so-called shrinkage estimator, right? We can compute this delta L in time that is linear in the dimensionality, quadratic in the number of samples, and we're going to use only LD amount of memory. And usually, if L, or the number of samples, is typically can be much smaller than the dimensionality of the model. So how are we going to do this? Well, we're going to do this in two steps. The first step is we need to assume, we need to get a really good covariance estimator, right? So if you think about the sample estimator of the covariance, I mean, it's not bad, it's unbiased, but unfortunately, it's not as great because we will not be able to invert it, right? If we have very few samples and very high dimensional parameter vectors, this thing is just not invertible. So one estimator that is really widely used in econometrics and biostatistics and is very well behaved in high dimensional settings is called shrinkage estimator, which is given on the slide. Essentially, it's a weighted combination of the sample covariance and the identity matrix, right? So it's always full rank, and it's going to be invertible and have all the nice properties. Now, these coefficients are a bit complicated here, and we had to come up with these coefficients because what we wanted to do is to be able to have a recursive relationship between these sigma I matrices, such that sigma I matrix based on L samples is equal to a low rank update, or rank 1 update, basically, to the sigma I L-1 matrix. And once we have this rank 1 update, now we can compute the inverse of the matrix using the Sherman-Morrison formula. Well, that's not all. So in fact, we can not only compute the full inverse of the matrix, but in fact, we can compute the matrix inverse multiplied by an arbitrary vector exactly and online as the samples are coming using a dynamic programming algorithm. It is based on Sherman-Morrison, but it requires a little bit of additional linear algebraic manipulation. It's only 20 lines of code, so it's extremely nice, and it solves this basically exactly. I'm not going to show this algorithm on the slide just because the math is a bit involved, but you can look it up in the paper. So once we are able to do that, right? So per sample, we'll have to compute only a constant number of vector multiplies, and as a result, we're going to get OOD compute and OOD memory on the client. So it's essentially pretty much identical up to the constant, right, to what federated averaging spends on the client. So it can be used actually on memory limited and compute limited, in memory limited, compute limited settings where clients are IoT devices or mobile devices. Right, so essentially we addressed all these challenges that I posed initially, and using these 3 steps, we should be able to estimate this mu. Now, if we put all pieces together, we can look at the final algorithm that we arrive at, which we call federated posterior averaging, right? And it has simply the pseudocode as given on the slide. So on the server, it essentially does the same thing as federated averaging, except that it expects slightly different deltas. And on the client, well, it runs SGD, right? But we use this SGD not for optimization, but rather for sampling. And then we somehow process the samples in order to obtain this delta I, right? So essentially, again, it's identical to the formulation of federated averaging by Reddy and Charles, where they show that you essentially run an optimizer on the client and then an optimizer on the server. So in our formulation, you run an MCMC sampling algorithm on the client and an optimizer on the server. And you can also use adaptive optimizers on the server, exactly the same sort of setup as Reddy and Charles. Now, another point that I wanted to make is that it also suggests that, you know, since it's so close to federated averaging, you can interpret federated averaging and in general, federated optimization algorithms, the majority of them, right, as doing posterior inference, right, under this Laplace approximation or under this like local Gaussian approximations. But they're estimating this covariance matrices with identities. Right? So instead of computing covariance matrix based on samples and using some, you know, good, well-conditioned estimator of the covariance, we can simply estimate it as an identity matrix.
Sorry, Maruan, there is a question. Let me try to unmute Konstantin. Maybe he can ask himself.
So I have a small question regarding previous slide. So about solving linear equations with a special algorithm with dynamic programming. So is it what is the complexity of this algorithm, which you mentioned 20 lines of code? Is it like NCube or something?
Right. So in this case, let me go back. Right. So if we have, so this is the time complexity, right? It's L squared D, where D is the dimension and L is the number of samples that we're going to get from the posterior. So if the number of samples is much smaller than D, right, which is typically the case, it's going to be essentially linear in the dimension. So in all our experiments, we used eventually a fixed number of samples, up to 10 or 20, and the dimensionality of the models was multiple millions.
Thank you.
Okay, so let's see. Okay, so right. So what I was saying is that federated averaging essentially implements this posterior inference, but uses biased deltas. So the way that deltas are computed is a bit biased. Now, if we just compare again everything on our toy example, right, with 2 client objectives and 2 parameters, and implement everything sort of exactly on NumPy, right? So this is what we get. We get the initial speedup for federated posterior averaging that is almost identical to federated averaging, and in terms of convergence, and it attains much better performance, much faster. Right? It's almost as good as mini-batch SGD at the end. Now there's this noise barrier, the sort of a region in the distance, in terms of the distance, or you can think of it in terms of the quality of the solution, right? Where sort of the noise that comes from the estimation of the mean and the covariance matrix actually plays a non-negligible role. So unfortunately, in this case, like to do better, right, and to go further down, you have to produce more samples and use more samples to estimate covariance and the mean. So the way that I like to think about FedPA and federated averaging is basically two sides of the coin in terms of the amount of computation that we can spend while being able to converge somewhere. So we can think about it in terms of bias and variance trade-off of the updates that the server collects and averages, of these deltas that clients compute. So here on this plot, I looked at, again, federated least squares in 10 dimensions and generated multiple synthetic data sets. And I've tried to compute the bias of federated averaging updates and federated posterior averaging updates compared to centralized gradient steps, right? So in this case, we can see that the more local steps federated averaging takes, the higher the bias and the lower the variance of the corresponding updates goes. The opposite is true for federated posterior averaging. So the more local steps we take, and in this case, we have to take way more local steps to actually reduce bias and variance by a significant amount where it's almost zero, basically the better the updates will be. So in a sense that explains why in previous papers people proposed to use clever learning rate schedules, right? So by manipulating learning rates or manipulating the number of local steps over the course of training, you can sort of adjust where on this curve you want to be, right? And for federated averaging. So for example, if you want to train faster, initially you can allow to have high biased updates, but make faster progress. Then eventually you'll have to sort of reduce it all the way and essentially run mini batches GD. For federated posterior averaging, the trend is opposite, right? Closer to convergence, you actually have to sample much more to have more accurate estimates of these covariance matrices, and in order to be able to converge again. So does this work in actual benchmarks? So we ran multiple experiments. I'm not going to go through all of them in the interest of time, but I'm going to go through just a couple. So here I'm presenting an experiment on CFAR 100, where the task was to classify between 100 of different classes. There were 500 clients. They were heterogeneous. It's a standard data set. And one trick that we had to use to actually make it work in practice with high dimensional models that are neural nets, right, which are very non-convex and very non-Gaussian, obviously, we had to run our algorithm in the burn-in, so-called burn-in phase, right? Where essentially federated averaging would run the same thing as federated averaging would do for some number of rounds. And after it sort of, converged to some basin of the local optimum that we're trying to sort of converge to, we can start sampling, right? And we can start computing these client deltas that are corrected. And as a result, we can see that the loss drops as we start correcting the client updates. And similarly, the performance and accuracy increases and converges to a better point after 1,500 rounds. So a more sort of noticeable difference can be seen on this Stack Overflow dataset, which has 300,000 clients, right? Which we ran only for 1,500 rounds, and we used, I believe, only 20 clients per round in this case. So only a small subset of clients was seen throughout training. This was a legit multi-label classification problem, right? So it was a logistic regression essentially. So it was a convex problem. And, we noticed that there is a more significant drop in the loss and more significant improvements in terms of the metric of interest. Okay, so just to summarize this part, what we introduced in this paper is a new perspective of how we can view federated learning, right? And we can view federated learning as an inference problem, and this allows us to design, new algorithms as well as reinterpret algorithms that we already know, and potentially sort of shed more light on their inner workings. And another point that I wanted to make is that, oftentimes when we hear about Bayesian machine learning or Bayesian deep learning, typically it happens in the context of quantification of predictive uncertainty, right? When we're trying to make predictions and be also know how certain or uncertain we are. So it turns out that it's also quite useful in distributed communication limited settings. not necessarily where uncertainty is necessary. In this case, we're not estimating any uncertainty, but we're still benefiting from this posterior inference. So I'll pause here for a bit before I move on to part 2 and to take any questions.
Just quick reminder, if you want to ask a question, just please post it to the chat or raise your hand and I'll try to unmute you. So yeah, okay, so we have one question by Slawomir. Let me just unmute him. So please go ahead, Slow.
Hi, I have a question about the choice of prior distribution. Can you choose priors to be different on local workers?
Yeah, that's a really good question. Technically, in this case, in our algorithm, we consider it prior to be uniform everywhere. So prior was the same for all the workers. You could potentially choose different priors and different workers. I think the way to think about it, in order to be sort of consistent with the global problem that we're trying to solve, you need to somehow account for it here, right? So when you pose the problem, right, you write down the global posterior, and it will be a bunch of local posteriors, right? But the prior sort of factors in. Here we just assume that prior is equal to 1 everywhere. If it's not equal to 1, you will have to sort of multiply this with the prior and make sure that the local posteriors account for it.
Thanks. And like if you have a local prior to be everywhere the same, like in some sense it affects the heterogeneity of data. So or like, am I viewing it incorrectly?
So I would say if you had a strong prior, right? If you had a strong prior, so let's say like highly peaked Gaussian prior around 0, right? Zero mean and some like narrow variance. I agree. So in this case, we had a uniform prior. So it's an improper prior. So technically it does not integrate to 1, but it's basically a constant which is equal proportional to 1, right? That you multiply. So essentially you don't impose any prior in our formulation right now. So we assume that there's no prior knowledge.
Thank you.
So there is another question from Shani. I'll try to unmute you.
Oh yeah, so thanks a lot, Maruan, for the great talk. So my question is very simple here. If you don't have too many clients, so it might violate the assumptions that you put at the very beginning, but if you don't have many clients and every single client has many data points, right? And it's very large size and you cannot really, well, it's very expensive to run these local iteration. What would you suggest here? Would FitBA still work?
Right. That's a great question. So basically, it's going to be not a cross-device setting, right? So at least if you're familiar with this paper called Advances in Federated Learning, right? Federated Optimization. It's a survey paper which was published in Frontiers in Machine Learning recently. So they distinguish between cross-device and cross-silo. Right. So sometimes you want to run federated learning across different organizations, and each organization has a lot of data. In that regime, technically, I would say you would be at a disadvantage to some extent if you want to run sort of sampling locally for many steps. Right. So in that case, maybe it's even better to run a distributed optimization, just take a single gradient step on every single client. Right, and then sort of send it over network. Because if the processing, the entire data set is very expensive, so potentially not taking many gradient steps is better. And the same applies to large models, right? If the models are extremely large, so taking the gradient steps on a very large model and optimizing a very large model could be quite computationally intensive. So these trade-offs, like in practice, you have to measure which ones apply and then decide which algorithm to pick. I should also say that FedPA is a very simple posterior inference that makes a lot of approximations, there's something called expectation propagation, which would be a generalized version of FedPA, which actually requires the clients to keep the state, right? And sort of use that state in order to be able to sort of converge to this posterior, in a sort of to a more accurate posterior. So yeah, so that's another way that you can approach this problem. And maybe the third way, I think, if you have very few clients, you can revisit these clients, and these clients have a lot of data. I would suggest probably using algorithms like scaffold or FedSplit, which were actually designed for the settings where you have to revisit all the clients multiple times. Clients, again, are stateful, so they have enough memory to carry this state, and then they can utilize the state to reduce the variance and actually make the algorithm converge to the correct optimum. I hope that answers the question.
Yes, got it. Thanks a lot, Maruan. Yeah.
There's another question from Peter, so please go ahead.
Hi, Maruan. Very nice talk. So I don't have a question about the actual talk. I may have some later. I won't take too much time. So I just had some comment about the introduction and about the motivation for this. So I understand you're working in the in the infinite kind of a cross-device setting, and you mentioned that whether you're working in the cross-device or cross-silo setting, these local type methods, Federated Averaging and so on, they do not work in a certain sense. They don't have the right fixed points, and then maybe one should reverse engineer what is the problem that these methods are actually solving. And you mentioned these papers by Patag and Wainwright and Charles and Konechny as pointing solving some of these issues. So I just have one comment. There's some prior work in the cross-silo setting where these kinds of questions have been asked and answered in different way. And I'll be just happy to talk to you at some point about that. But I'm not aware of anything in the cross-device setting, which is the setting that you're studying.
Right. Yeah, I'd be very curious to learn about the prior work on the cross-silo setting. Yeah, and I should say, I think the third paper that is related to, which is basically essentially algorithmically the same as this FedSplit of Patag and Wainwright, is Scaffold, which comes from Google and was published slightly earlier than FedSplit. That also sort of works really well in the cross-silo setting. But perhaps the work that you mean is it probably earlier?
Yes, I want to talk about it here, and so on. It's not quite appropriate. Just kind of a plug in there for maybe some further discussion. Thank you.
Yep. All right. So
maybe I will have just one quick question. Like you said, like you do a lot of approximation and stuff like that during this. But so just a question is, can you actually guarantee convergence once you assume that everything is Gaussian? You have a nice strongly convex function. So can you, and then let's say you run enough local steps, so the approximation is actually good enough. So can you then guarantee the convergence?
Right. So you can. So in the paper we don't show that, right? But you can roughly guarantee, right? So your conversion, you will converge basically to a neighborhood of the optimum that you'd like to converge to, and how vast or how small this neighborhood is going to be it will depend on the variance as well as the bias of the model. So if in the long run, right, of these sampling methods, eventually both variance and bias will go to zero. So at that point, you can certainly guarantee. How fast and how many steps you need to actually take, that's a great question. So I think that requires characterizing actually the sort of properties of these Monte Carlo samplers. And that's a little bit non-trivial to do.
Thank you.
Okay, so I don't have much time, but I'm going to move on to the second part, I think, which I'll basically go through a bunch of highlights. And the second part is titled on data efficiency of meta learning. So this is sort of unrelated to the first part, where we focus on the standard federated learning setting. Because it focuses on personalized FL. Right, so why personalized FL? I think one of the papers that came out, probably preprint that came out in the summer last year, and that's not, I should say, that's not the only paper that argues for personalized FL. There were a lot of prior work, but interestingly, what I found interesting about this paper is that they have this interesting plots that show how good or bad the average, or this global federated model that is learned with federated averaging or some other algorithm, if you look at its performance on each individual client, right? And you can look at the local accuracy, right? And what is local accuracy here is that if you take just the data that the client has and train a single model just on that data, what is the gap between this the accuracy of the federated model compared to that local model? And we see that for certain tasks such as work prediction, there are so many clients, there's a long tail of these clients where for them it's just better to not participate in federated learning. Right? So it sort of defeats the purpose of federated learning in a sense. And the authors, sort of the bottom line of the paper is that the models obtained by federated averaging and similar algorithms are actually worse off than purely local training. And I'm pretty sure it's going to be the same result even if you use FedPA or many other algorithms. So the authors of this paper, and I would say, in a sense, it's a position paper, and they argue for the need of personalization so that the community has to focus a bit more on personalized federated learning. Now, the simplest way to personalize these models and to make these models better than just the average model returned by federated averaging is consists of two steps, right? First, we can run federated averaging for a bunch of rounds. We get a model that is on average really good. And then at test time, if the client has some supervised data, we can just simply take that model and fine tune it on the available labeled data, right? And that works pretty well, actually. That method in meta learning literature is known, or in few shot learning literature, is known as so-called reptile. And they came up with this name just as a, an acronym. It's not even an acronym, as opposed to another method, which is an acronym and called MAML, which I'll overview in just the next slide. But the idea of this approach is identical to sort of running federated averaging and then fine-tuning on the available labeled data at test time. Right, and of course, like when you fine-tune on the labeled data at test time, you don't test on the same data you test on a held-out test set. Right, so just to give you a little bit of background, the question that arises here, right? Like if this already exists in meta learning, can we just take some of the methods from meta learning and repurpose them for personalized federated learning? And there's a lot of works that actually do study that. In fact, they do study this model agnostic meta learning in the federated settings. And just to give you a little bit of background on what is model agnostic meta learning, well, in meta learning and few shot learning, we no longer talk about clients, but we talk about so-called abstract tasks. So each task is associated with a small data set, and would like to find a model and be able to personalize models to each individual task so that after personalization, these models work really well. So the formulation is given, the mathematical formulation is given on the slide. That notation is not as important here. So what is important is basically the intuition that this model agnostic meta learning, or MAML, is following, right? It tries to basically to learn, instead of learning a model that does on average really well across all the tasks or all the clients, it tries to learn a model that is a good enough initialization for fine tuning, right? And basically you're trying to arrive at a point in the parameter space such that after a few gradient steps of fine tuning on the tasks that are coming from the same distribution, you obtain a model, this theta I star, which is good enough for that specific task. And you can basically formulate this with a new loss function that these authors proposed, and sort of optimize these loss functions directly for initialization for fine tuning instead of trying to get a model that is average, that is good on average. Now, in our work, in our paper that will appear at AI Stats this year, we asked the following question. So how can we characterize data efficiency of modern meta learning algorithms? And why is this important? Well, we argue that in many practical settings, such as personalized federated learning, we have a limited number of clients, we have a limited amount of data on clients, and we have a limited amount of compute per client. So it is important to know how many of these clients and how much data per client we need in order to attain a really good sort of performance post personalization, after personalization. So that's the motivation, and we approach this both theoretically and empirically. So we derive basically generalization bounds for popular modern meta learning algorithms, and we empirically validate predictions of our theory. So our generalization bounds use so-called stability theory, and I'm gonna, mostly skip ahead and just present some of the results that we get. So first, we identify two types of objective functions that are commonly optimized in meta learning, and essentially I already named the two of them. Right, one of them is used by MAML, and the other one is used by Federated Averaging or Reptile. So the first one, which is used by Federated Averaging or Reptile, is Empirical Estimator of the transfer risk, where we simply take all the data on each client at training time. We're going to try to optimize and get a local model, right? And essentially, when we do this averaging, we're approximately optimizing this empirical risk, right? Which is given on the slide. And this empirical risk for a single client, we essentially trying to optimize expectation of this empirical risk. Now, MAML does something smarter. MAML takes the whole data sets on each client and splits it into two sets. One of them called the support set, and the other one is called the query set. And what it does, it trains local models on only a subset of the data. Then it computes the loss on the held out set, which is the query set. And then it sort of averages these losses and tries to optimize them with respect to the initialization of the model. Right. So it's a slight difference between the two. The difference how you separate the data and on which subsets of the data you compute the, you sort of personalize the model in this inner loop, right? And on which subset of the data you compute the loss. And example methods that we consider in our paper are essentially Reptile and Federated Averaging and MAML and prototypical networks. So the main results that we get is the following two meta-generalization bounds. So what is a meta-generalization bound? What it says that the difference between the loss that we're going to obtain at training time and the expected performance on new tasks sampled from this data set is bounded by the following quantity on the right-hand side, where O is the big O notation. And so there's so-called first term, which depends on the stability, right, on the algorithmic stability of the outer loop. And the second term that depends on the algorithmic stability of the inner loop. So what is stability? Stability means that if we run the algorithm and the inner loop on the same data, but without a single data point, in expectation over all the data points, the change in the model will not be as drastic, right? So the more stable the algorithm, the more local data we have, essentially, the more stable the algorithm is going to be. And different algorithms can be, can exhibit different levels of this algorithmic stability. So this is a tool in, theoretical toolbox that allows us to bound, to provide generalization bounds. Interestingly, that for MAML and protonets and all other methods that actually optimize this loss on the held out Q set, this component vanishes. Right? So the inner loop stability is gone, only the outer loop stability is present, and we see that this must have some kinds of implications. Right? So the implications that we derive from this in the paper is, well, the first one is that as the number of tasks goes to infinity, right, the generalization error essentially for MAML and other types of methods like this should go to zero. So we should really not be able to distinguish between the methods trained on very, very many tasks. Now, in typical benchmarks that people use to benchmark meta learning methods and then sort of compare them and say which one is better than the other and which ones people should use in practice potentially, right? Typically you train on an uncontrollable large number of tasks, right? So one of the arguments that we make in the paper is that you have to train on a limited number of tasks and a limited amount of data per task in order to be able to distinguish between different methods and that sort of limited supervision regime. And we see that the dashed lines are the numbers reported in the original papers for MAML and prototypical networks, right? And they're literally indistinguishable. If we do limit the number of training tasks, though, we can measure their task accuracy, and we can see, sort of drastic difference between the two methods on two different to different benchmarks. And benchmarks here are 5-way classifications with either one shot, and one shot means that we have one data point per class at adaptation time, right? And 5-shot where we have 5 points per class at adaptation time. So interestingly, for these two methods, actually, the trends reverse depending on how much data we have at adaptation time, which is completely invisible if you look just at the numbers typically reported in standard meta-learning papers. Now, the second thing that we observe is that federated averaging and Reptile do have this additional additive term, which means that the bounds, well, on one hand, the bound may not be as tight, but at the same time, it implies that there could be potentially worse performance. These methods should exhibit worse performance unless there is a sufficient number of samples per task that is provided in meta-training time. Now, finally, our final observation is that the meta-generalization of these methods depends on the algorithmic stability constants, right? Which I sort of hide on my slides, right, in this big O notation, and on the stability of the inner and outer loops of our meta-learning algorithms. And what we hypothesize is that by actively selecting data, right, in the inner and outer loops, we can improve potentially stability as well as a consequence generalization, right? And we run a couple of experiments. So the first one to confirm hypothesis number 2, right? So that Reptile or federated averaging with fine-tuning essentially requires more data per task or per client, if you will, right, in order to be able to attain better performance. And the second hypothesis is that if we select this data actively at meta-training time, right, we can actually improve performance in this for active selection. The bars are green, and for random selection, which is standard, the bars are blue. And finally, we also try to sort of evaluate all the methods and benchmark them across a variety of different data sets, as well as a variety of different settings, and see how they behave when we have a limited budget, limited labeling budget, and we allocate this labeling budget between different amounts or different numbers of labeled data points per tasks, as well as different numbers of tasks that are available at training time. So you can see that trends, interestingly, for Mammal and Reptile are sort of reverse on some of the data sets that are easy to learn from or easy to fit. Some of the data sets, the trends are sort of indistinguishable. And you can see much more results in the paper. So I'll probably stop here and